Okay, so I'm trying to do this educator series, grokking the coding interview, patterns for coding questions, in which they go through these patterns uh, and then try to solve these problems, which could be solved by knowing this one pattern. For instance, depth first search can be used to solve binary tree path sum, all paths for a sum of path numbers, path with given sequence, count paths for a sum, and some few other problems. So if you know DFS, you can solve binary tree path sum. And let's just get right into it. So what is the binary tree path sum problem? It says given a binary tree and a number s, find if the tree has a path from root to leaf such that the sum of all node values of that path equals s. So if s is 10, then we know 1, 3, and 6 makes 10. So that means yes, this tree has that path. If s is 23, then 12, 10, and 1, we know this tree has that path. But 16, this tree doesn't have it, so it'll return a false. They also give you this sort of pattern, and you can just copy this thing. I don't like to code here. I prefer Sublime or something else, like some IDE. You know, it's close to Sublime. Let's see. Okay, so I'm gonna do a quick class binary tree path sum, and yeah, okay, so this is what they're doing. Let me just call this binary tree path sum. So this is what they have given as a template to us. They've created a tree node, which basically will represent each node in the binary tree, which will have a value and a left and a right. This is pretty straightforward. Uh, and then they have a class called binary tree path sum, in which they pass a root node which has left, right, left, left, right, left, right, right. So I think it looks something like it's like a root node is 12, and then there is a 7, and there's a 1, then there is a root left. 7 has a, just do this. Yes, 7 has a 9 to the left, and then there is like a null, I think. And then root's right has a left, which is 10, and root's right has a 5. So something like this. And basically this node ends here. And what they want us to do is they want to pass this path, this tree, and they're going to find whether 23 or 16 are present in it. So it looks like this is what they're talking about. This is the tree that we've given, and we have these two inputs. Uh, we have this method which we have to write code for. So it looks like static boolean. So we have to return true or false whether the path is there or not. We are given the root node and we have the sum. Okay, so we do know that they're saying that if we had no DFS, we could be able to solve it, and I can already see how, because we have to calculate a path from node to the end to the leaf. We know that DFS does that. DFS, for people who don't know how DFS runs, it's basically a traversal technique of binary trees in which we go till the bottom or to the we start from the top and we go to the bottom, and then we go back up and do the same for the next node. Uh, in comparison, BFS, breadth first search, is another way of traversing, which is uh, also called level order. And what that does is it goes from left to right. So instead of how DFS goes vertically, BFS goes horizontally. So 1, 2, 3, 4, 5, 6, 7. That would be BFS. So let's just go down and so we know that DFS means that we have to go 12, 7, 9, or 12, 1, 10, or 12, 1, 5. So if we do DFS, we can do this. So it seems pretty forward right now. Another thing about DFS is we use stacks to kind of do the traversal. BFS uses queues, so you can look it up. Uh, so if I Another thing about stack is like if we just write a recursive algorithm, we don't need stack data structures. Iterative would need a stack data structure, but if we do it recursively, we don't need a stack data structure. So let's see what we're trying to do. So we want to see whether the sum exists or not. I think it looks straightforward. So we can calculate whether the sum, when the sum reaches 9, whether it stays 0 or whether it uh, becomes greater than 0 or less than 0. So if I have a sum 23 and I subtract 12 from it while doing DFS, and then it'll become 11, and then if that 11 is sent to this node and 1 is subtracted, it becomes 10, and if it back 10 node, it becomes 0. So if it becomes 0 at this point, then that means we have found a path. So it's simply forward. So what they're saying is that if sum is equals to 0 at leaf node. So basically we have to find two things, that the node is leaf and we have to find that the sum is 0. So if sum is equals to 0 and root dot left is equals to null, or root dot right is equals to null, that means this is one of the nodes that we have to go. So for 9 we know that its left and right are null. For 7 we know its left is 9 but right is null. So we can also calculate this node, 12 to 1. I think so. Okay. So if we have a root node and null or right is null, then return true, and else we can just do a return as path root dot val, sorry, sum minus root dot val. sorry. So root dot left will go down another path and we'll check sum minus root dot val. So if either we have a path like that on the left side or we have a path like that in the right side, then so what we're doing is first we're checking the current node, which is like 12 in this case, and we're seeing if that, so this is like a base condition. We know recursive algorithms has to have a base condition which basically gets you out of the recursion. Like if we reach the end of the node, we can do that by reaching, we can just check it whether the end has been reached, because otherwise it'll just go on in an infinite loop. So so this is the base condition. So when we have reached sum 0 and root is equals to this. If it hasn't been reached, then it goes. But yeah, I think I see a problem here. If sum is not equals to 0 and root left, one of them is null, then if both of them are null and sum hasn't been reached, then it will go just gonna send this path. I don't know, maybe. Okay, so what I'm trying to do is I'm doing root left, and then I'm gonna delete. So 12 minus 23 minus 12 will become 11, and then that 11 is sent down the left node. It will fail here, but in here it will subtract by -1. So either side basically is creating a path, it will return a true. Otherwise, it'll return a false. Uh, I think I can also do, I think I need to also do this. I need to check whether the root is null or not, because if it's null and the sum is still not, in this case, if it's null and the sum hasn't become 0 yet, we know it's not going to become 0. So we can return false. Okay, so this is just redundant. I think this should be able to work. So another good thing that they do in interviews is they want you to go and run your algorithm on whatever you get. So let's run this on 12, 7, 1, 9, 10, 5. So we have like 12 and we have a sum 23. So we'll see if 12 is null or not, which it's not, so it's not going to return false. Then we'll see if sum is 0 or not. Sum is not 0, and because we haven't subtracted anything, so it's going to pass that. And then it's going to say, okay, root dot left, and sum will pass 23 minus 12. So what's getting passed here is 23 minus 12, 11, and we'll pass it to the root left. Root left is 7. So we'll go inside here and say, okay, it's still not 0, and so it's gonna go back down here again. This time we're gonna go root left again, but yeah, and 9 is roots left. So, but we'll do, what do we have left? We have 11, so we'll do an 11 minus 7, and which will make it 4, and then it'll go down again because it'll pass all this stuff, and then it'll go, and we'll subtract 9 from um, 4, which will send it into the negative, and in the end we'll reach a root where root becomes null and will return a false. But in case of root dot right, 12 1, 12 gets subtracted, and then 12 becomes 11, then 1 gets subtracted, and then 10 gets subtracted. Yeah, this seems pretty tight to me. Let's see if this works. So I can just copy the stuff because they have pretty much the same definition as us, since we pretty much picked it up from there. Okay, let's see if this works. Really hope it does. Otherwise I have to make this video again. Okay. False, false. Okay. This is saying to me that it is false in both the cases. It shouldn't be false. It should be false for 23, but not for the other one. Okay, so what did I do wrong here? Huh. I think I know what I did. So if I do this, that's not what we want. We want it to be equal to the last node's element at the asked element. Then root dot null and root dot right dot null will work. Okay. Let me just check this really fast. I think this will fix it. Yes, it fixed it. Okay. Yeah, that was stupid. Okay, so what I did here is I was checking 0 in the last node. But the thing is, in the last node, in this example, we are still at 10. So the sum is 10. It's not going to be 0, it's going to be 10. So we got to check it to 10 rather than 0 because we haven't subtracted 10 yet. Because we are at the leaf node and we are checking whether the leaf nodes left and right is null or not. But at the same time, we are forgetting that the leaf node's value right now hasn't been subtracted from the sum. So sum has to be equal to the leaf node. Okay, so seems like this solves it. And yeah, so if you know DFS, this is pretty much DFS. It's just a modified version of it. So we're not exactly we are traversing, but we are doing additional stuff here. It's basically finding whether the path is returning true and false. So yeah, this is how it's done in binary tree path sum. Uh, okay, one last thing. They're talking about like the time complexity. Uh, I think this is okay. I think it's going to be ON because we're touching each node once. There's no multiple going. Um, but yeah, this is like a very good course if you want to take it. Oh, looks like they're doing the same thing. Oh, yeah. See. Oh, they're using my technique. Interesting. Okay. I guess I've done it probably before. So, okay, so the time complexity is ON. Space complexity is going to be ON because, again, we are using the stack in the system. It's a recursion stack, but it's still taking space. So this is how this is DFS and binary tree path sum. Thanks.